Welcome back to the deep dive. Today, we're digging into some really dense configuration guides. Highly technical stuff, focused on optimizing how content gets delivered in complex networks. We're going to try and boil it all down to the essential knowledge you need, the stuff that actually saves money.
Absolutely. The sources we're looking at, they're all about IPv4 multicast VLAN traffic reduction techniques. And, well, this deep dive is pretty necessary because, honestly, when you send high bandwidth stuff like video streams to lots of users, the default network setup, it's almost designed to fail. Spectacularly sometimes.
Wow, okay. Designed to fail. That sounds intense. What's the core problem? What's this chaos engineers are fighting?
It's flooding. Plain and simple. Think of your network switch like maybe a slightly overwhelmed post office worker. If one person sends a package meant for one specific address, but the worker doesn't really check the label carefully, their easiest route is just to duplicate it and send it to every single mailbox in the entire town.
Okay, that's incredibly wasteful.
Exactly. In networking, when a switch gets a multicast packet, think of that as our package. It often treats it like a broadcast. It just forwards it out to every single port in that VLAN. Wastes bandwidth, power, processing. It's a mess.
Right. So we need that switch or that postal worker to be smarter, to actually read the address. Okay, let's unpack this. The foundational tool, the starting point for stopping this chaos, that's IGMP snooping.
That's the one. IGMP, the Internet Group Management Protocol, it's basically the standard language clients use. Your computer, an IP camera, maybe an IPTV box. They use IGMP to tell the network, hey, I want that specific stream. They signal they're interested in a particular multicast group address, usually in that 224 to 239 range for IPv4.
So IGMP is the client saying, I want this, and IGMP snooping is the switch actually listening.
Precisely. It's a layer 2 thing. The switch isn't routing, but it is snooping. It's monitoring those IGMP messages, those membership reports. And based on that, it builds this dynamic table. It maps the multicast group to the physical ports that asked for them. So instead of flooding everywhere, it sends the traffic only where it's wanted. It's probably the biggest single way to save bandwidth and money on your local network.
Okay, and you mentioned this relies heavily on hardware. Something about memcache entries in the specs. Why are those limits important?
Yeah, the memcache. It's crucial because speed is everything, right? Especially for video. These memcache entries are like dedicated fast lane memory right on the switch hardware. Shortcuts, essentially. They store the decisions. Group X goes to port 5 if the switch runs out of these. And the sources show they can cap out maybe 8,892 entries on some platforms, like the RKey SICX series. Depends on the profile.
Yeah.
Well, if they run out, the decision gets pushed up to the main CPU.
Which means delay. Latency. Bad news for video.
Exactly. Fatal for video quality, potentially. So those hardware limits matter.
Got it. And the technology is evolving. IGMP v3 seems like a big step up. Introducing source-specific multicast or SSM. What does v3 let us do that v2 just couldn't handle?
Well, it's about control. A massive increase in control, actually. With V2, a client could only say, I want stuff sent to Group X. Pretty general. But V3, the client can specify the source too. They can use an includee list, like, I only want traffic for Group X if it comes from Server A or Server B.
Okay. Or the opposite.
Or the opposite, using an includee list. Give me Group X traffic from everyone except don't give me anything from Server C.
So it's like asking for a specific coffee, but only from your favorite barista. That level of control must be huge for security, right? Stopping bad streams.
Absolutely. Security, preventing errors. It adds nuance you really need for modern applications. It's definitely where high-performance networks are heading. More precise control.
Okay, so we've stopped the initial flooding. Clients have joined using IGMP. But how does a network keep track? How does it know when someone leaves so it can stop sending the stream? Needs active listening, doesn't it?
It does. And that's where the IGMP querier comes in. You need one active querier in each VLAN. Its job is to periodically send out these general query messages asking, hey, is anyone still listening to these groups? If a device doesn't respond within a certain time for a group it was part of, the switch assumes it's gone. And it takes that port off the list for that specific multicast stream.
And you mentioned if multiple devices could be the querier, only the one with the lowest IP address actually does the job.
Correct. It's a simple election process, keeps things tidy, prevents duplicate queries flooding the network.
Makes sense. Now, fast leave. That sounds important. If someone stops watching a live video, you can't wait ages to cut the feed, right?
Definitely not. Waste of bandwidth. Fast leave is critical for that instant reaction. With IGMP v2 fast leave, if the switch gets a specific leave message from a client, it just immediately stops forwarding that group's traffic to that port. Bam, done, instant relief.
But I saw something interesting, maybe a bit confusing, with IGMP v3. Since V3 tracks source and group, why do the docs sometimes mention a default wait time, like 60 seconds before stopping traffic unless you change it? That sounds slow.
Yeah, that's a really critical point for anyone configuring this. It can seem counterintuitive that default wait exists mostly for resilience. Because V3 is tracking specific sources, the network wants to be really sure the client is gone, not just a temporary blip or maybe the source path changing slightly. But you're right. For real-time video, 60 seconds is an eternity. You absolutely configure that down or turn it off. It's a trade-off you have to actively manage based on the application.
Precision is key, and the sources mentioned a specific application, SDVoE, software-defined video over Ethernet.
Ah, yes. SDVoE is a perfect use case. Professional AV distribution, zero latency needed, super reliable streams. It relies heavily on really tight IGMP snooping. You'll see things like automatic configuration of edge ports or specific commands like multicast as Devo being used. It's making the network act like a high-end AV matrix switch, essentially.
Very cool. Okay, so that covers managing traffic inside the local switch domain.
Right. But often that traffic has to come from somewhere else, maybe across the building or even from the internet.
Yeah.
It needs to cross layer 3 boundaries, usually through a router, and routers often use PM protocol independent multicast.
Okay, so the switch needs to talk to the router, basically. Coordinate its snooping intelligence. Which brings us to PMSM snooping.
Exactly that. PMSM snooping means the switch is now listening for PIM messages, specifically join and prune messages from the router. It integrates this with its IGMP snooping knowledge. The switch knows if anyone local needs a stream, thanks to IGMP. PMSM snooping lets it tell the router upstream, hey, nobody on my patch needs that stream anymore.
So the router can prune or block that traffic further up the chain, maybe even before it hits this part of the network at all.
Ah, that's a big difference. IGMP snooping saves bandwidth locally on the switch ports. PMSM snooping saves bandwidth upstream on the links back to the core, maybe even the WAN connection. Precisely. It stops unwanted traffic much earlier. Huge efficiency gain for the whole network. Though, like always, there are catches. The guides often mention PIM-SM snooping isn't supported on the default VLAN, for instance. So, configuration details matter. It adds a layer you need to manage.
Got it. Okay, let's pivot slightly. There's another tool specifically for things like IP television, IPTV deployments, multicast VLAN registration, or MVR. Sounds like it tackles a specific kind of large-scale problem.
It does. MVR is really designed for scenarios like IPTV or maybe campus-wide video distribution. Think about having hundreds of TV channels. If you have subscribers in, say, 20 different VLANs, without MVR, you'd potentially have to duplicate every single active channel stream into all 20 of those VLANs. A nightmare.
Right, massive duplication. So how does MVR fix that?
It uses a dedicated VLAN called the multicast VLAN or MVLAN. All the source traffic, all the TV channels flow only on this single MVLAN. Then you have specific port roles.
Okay, let's define those roles clearly. There's the MVLAN itself.
Right, the central channel highway. Then there's the MVR source port, or SP. That's where the channels enter the MVLAN. And finally, the MVR receiver port, or RP. That's connected to the end user, the subscriber's set-top box or PC. Crucially, that receiver port is in a different normal user VLAN.
Okay, so all 100 channels are on the central MVLAN. A user in, say, VLAN 10 requests channel 5 using a standard IGMP join, and MVR cleverly copies just channel 5 from the MVLAN down to that specific user's port in VLAN 10.
Exactly. It avoids duplicating everything everywhere. The traffic flows once centrally, and it's selectively delivered only when requested via IGMP from a receiver port. It solves that bulk distribution headache very neatly.
Built for scale. Makes sense. But a really critical point from the sources. PIM is not supported with MVR, and MVR isn't supported with PIM. They're mutually exclusive. Why? What's the trade-off in engineer faces there?
Yeah, probably the biggest constraint to understand, they solve related but ultimately different problems in ways that conflict. MVR is fundamentally a Layer 2 solution focused on efficient replication within a single switch or Layer 2 domain, great for local delivery. PM, on the other hand, is a Layer 3 routing protocol. It's designed to get multicast traffic across different networks, different subnets, maybe across the whole enterprise. Because MPR centralizes all sources onto that one MVLAN, it essentially bypasses the Layer 3 routing logic that PIM needs to function.
Ah, okay. So you choose based on scope. If it's local, high-volume video in one L2 domain, MVR is efficient. But if that traffic needs to be routed across subnets, you need PIM, and you stick with standard IGMP snooping.
That's the choice, fundamentally. MVR for localized efficiency, PIM for routed distribution. You can't really have both working together on the same traffic flows.
This has been definitely a deep dive. We've covered a lot of ground for reducing that network chaos. We hit IGMP snooping for managing local clients joining and leaving, then PMSM snooping for controlling traffic further upstream towards the router, and MVR as that specialized tool for things like IPTV consolidation. So, wrapping this up, what's the key takeaway for someone planning their next network design or upgrade?
It really raises an interesting question, doesn't it? With efficiency being key, but also precision and security becoming more critical. Which approach is, maybe, more future-proof? While MVR is fantastic for its niche, that bulk video consolidation, it feels like IGMP snooping, especially with the advancements in V3, holds more long-term promise architecturally.
Because of that source-specific multicast capability, controlling not just the group, but the source.
Exactly. SSM, using those include and exclude lists, it pushes intelligence to the edge. It allows for much finer control over quality of service security, making sure clients only get traffic from sources they actually trust. So thinking ahead, here's something maybe for you to mull over. If IGMP v3 already lets us filter by source, what's the next layer of control? Could we see future protocols or extensions allowing filtering based on, say, traffic characteristics? Imagine a client being able to reject a video stream if its frame rate drops too low or its latency goes too high, based on rules it sets.
Huh. Auto-regulating quality based on the content itself, not just the source or destination.
Right. Moving beyond just directing packets towards intelligent content-aware forwarding. That feels like the next frontier after source control. Something to think about anyway, as you decide how smart you want your network's forwarding plane to be.